Momentum is one of those things that people find a tad confusing, but it really oughtn't be. Momentum is equals to mass times velocity. Now mass is measured in kilograms, velocity is measured in meters per second. GCSE people, sorry that I write it like that, we can write it like that as well. So that means momentum is merely going to be kilogram meters per second. But those of you doing A-level, you might know that the alternative unit for the Newton is the same as kilogram meters per second squared, because that basically force equals mass times acceleration. To get from here to here, all we have to do is times by seconds. So kilograms meters per second is exactly the same as Newton seconds. So if you see the unit Newton seconds, you know it's exactly the same as kilogram meters per second. That's the unit for momentum. What actually is momentum, if you want my personal definition, is how hard something is to stop. The more momentum something has, the more force is needed, or the longer time is needed to actually stop it. So say that you had a choice of getting hit in the chest, and you had a bulletproof vest on, don't worry about it, with a bullet out of a gun, or a train. Now the mass of the bullet is 5 times 10 to the minus 3 kilograms. In other words, it's 5 grams. It's travelling at a speed of 200 meters per second. The train, on the other hand, is travelling pretty slowly. It's sort of just setting off, as it were. 1 meter per second, but its mass is 10 tons. 1 times 10 to the 4 kilograms. What's the momentum for each of these? Well, we use m for mass, v for velocity. The letter that we actually use for momentum is p. Generally little p, because big P is used more for pressure. So what do we have? 5 times 10 to the minus 3 times 200, and that gives us a measly 1 Newton second of momentum, or kilogram meters per second. I'm just going to use Newton seconds, save me my Sharpie ink. On the other hand, we have 1 meters per second times 1 times 10 to the 4, so that's actually 1 times 10 to the 4 Newton seconds of momentum that the train has. So even though the bullet is travelling so much faster, 200 times faster, it has a tiny momentum compared to the train that's just trundling along. Which one's going to send you flying more? The train definitely will. If both of these things transferred all of their momentum to you, in other words they both stopped when they hit you, the bullet might send you flying a little bit, the train is going to send you absolutely flying for miles because it's got a lot more momentum to give you. Now when things collide in any way, shape or form, momentum is always conserved. Now we should probably say that total momentum is always conserved. In other words, if you take the momentum of one thing and another thing that are crashing into each other, the total momentum of both of those things, or all of those things, is always going to be the same. Now there are two types of collisions. We have elastic collisions and we have, shock horror, inelastic collisions. The only difference between these two, momentum is always conserved in both of these things, but in elastic collisions, total kinetic energy is conserved, and in inelastic collisions, total kinetic energy, you guessed it, is not conserved. So don't forget that kinetic energy is half mv squared. I'm just going to write it as EK. You could get asked, here's a collision, calculate what's going on with the speeds and check if it's elastic or inelastic. So let's have a look at an example of a collision then, shall we? Let's go with coupling. This could be two train cars coupling together. One has momentum before, the other one has momentum before, and then afterwards they have the same momentum added up. But seeing that we're talking about coupling and couples, let's go with a couple of figure skaters. Now what I do is split my page in half, before and after the collision. Before, what we have is the girl skating towards the guy, and he's ready to catch her, and he's going to lift her, and they're going to go off together like so. So there they are. Afterwards, let's say that the guy is also going that way as well. To begin with, we're going to call this girl M1, and she has a mass of 60 kilograms. The guy, M2, has a mass of 80 kilograms. What do we know about afterwards? The mass of both of these put together, so I'm going to put M12, not M12, but M12, that's going to be equals to 140 kilograms, because they've now coupled together. They're going off together. What do we know about the speeds? Well, we know that from SUVAT, when we have an initial speed before and a speed afterwards, generally we use U. So I'm going to put U1 and U2. The girl to begin with has a speed of 5 meters per second. The guy only has a speed of 2 meters per second. Afterwards, they've got a speed going off together, so I'm just going to put V12. That's what I want to find out. So we need to come up with an equation for this. Now we know that the total momentum before equals the total momentum afterwards, so we can say M1, U1, that's the momentum of the girl, plus M2, U2, that's the momentum of the guy, equals M12, that's the mass of both of them before, times V12. That's the velocity of them afterwards. Pop some numbers in. We have 60 times 5, brackets that, plus 80 times 2 equals 140 lots of V. I'm just going to call that V. I can't be bothered to call it V12. All you have to do then is rearrange it to find V. And we end up with a speed of 3.29 meters per second. All we did was figure out how to represent their momentums, their momenta before. M and U, M and U. That's the total momentum before the collision. This is the total momentum after the collision. Make an equation, rearrange it, and find the unknown. So that's coupling. Let's have a go at another one. Recoil, say from a gun, like we were talking about earlier. We have before, and we have after. Before, we have somebody with a gun, and nothing's moving. How much momentum do we have? 0. We have no momentum. Afterwards, the bullet's gone off in this direction. And the shooter and the gun are obviously going to go backwards because of the recoil. How much momentum should we have afterwards as well? Total momentum? 0. Still. That must mean that the momentum of the bullet plus the momentum of the shooter and the gun must add up to 0. Does that make sense? Yes, because we know that the velocity of the bullet is positive, the velocity of the shooter and the gun is negative. So adding up momentum plus a negative momentum, they should cancel each other out and they add up to 0. So all I have to say is we have a mass here of the gun. I'm going to call that mg. And we have the velocity of the gun as well, and the shooter as well, obviously. And we have the mass of the bullet, mb, and the velocity of the bullet as well. Making an equation for this, we just say mg vg, that's the momentum of the shooter and the gun, plus the momentum of the bullet equals 0. Now you've got to be careful with the whole negative velocity thing. There is a bit of a shortcut that I like to use. I just like saying, well, I know the momentum of the bullet is going to be the same as the momentum of the gun and the shooter afterwards. This isn't quite true because, of course, one of these is going to be negative compared to the other velocity. But so long as you remember that one of them is going one way and one of them is going the other way, and let's be honest, you can remember that, then you should be fine. So let's use the same mass of the bullet. I'm going to say that that is 5 times 10 to the minus 3 kilograms. And the speed of the bullet, again, is 200 meters per second. Now, though the mass of the gun and the girl is 65 kilograms, so I want to find out the recoil speed of them going backwards. All I want to do is rearrange this to find that speed, that velocity. And we end up with 5 times 10 to the minus 3 times 200 divided by 65. That gives me 0.015 meters per second. Not going back very fast. It is only a small bullet after all. So that's recoil. We also have rebound. Now, when snooker balls hit each other, they have two options. Well, three options really. The cue ball can hit the other ball and it can just stop dead. The cue ball can carry on going if you put some topspin on it, or it could come backwards if you put some backspin on it as well. The problem with those is that they do affect whether the collisions are elastic or inelastic, but let's not worry about that for now. Let's just worry about the actual momentum side of things. So we have before and we have after. So we have our cue ball coming in, and that's going to hit the red, which is staying still at the minute. Afterwards, let's say that our cue ball goes backwards. We put some backspin on it, and the cue ball's going off in that direction, hopefully going into the pocket. Again, we have M1, U1, M2, U2, M1, V1, and we have M2, V2. Now, no matter what is going on with this whole situation, we can say that M1, U1, M2, U2 equals M1, V1 plus M2, V2. Let's go back to Newton's second law. That is F equals ma. What is acceleration? Well, it's change in speed over time. So I could put m delta v over t. Actually, it doesn't have to be v that's changing. It could be m as well. So I'm going to put a delta in front of both of those two things together. This, if you will, is the more accurate version of Newton's second law. This is saying that force is equals to the rate of change of momentum. mv, momentum, divided by t, delta, change in momentum over time. Anything divided by t is the rate of the change of that something. I could actually write this as then v delta m over t. Same thing, it just depends on what's changing. Is it the mass that's changing or the velocity? Generally, you will never have a situation where both the mass and the velocity are changing at the same time. It'll either be the velocity changing or the mass that's changing. So on cars, you have something called crumple zones. If you're in a car crash, your momentum is going to come down to zero every single time. That's not going to change whether you have a crumple zone or not. But what does a crumple zone do? It increases the time of the collision. What does that mean? If you increase t, that means that the rate of change of momentum is lower, so therefore F is lower. If you get fired out of a cannon, then you've got a choice of hitting a wall or hitting a nice big net. Your momentum is going to come down to zero either way. Which one's better? Of course, the net is, because the time for that collision is going to be longer, so the force you feel is less, and so you'll probably survive that. Let's very quickly look at our ball that's hitting a wall again. Like so, and we have it going in here, and we have it coming out there. It's going in with u, and it's coming out with minus u. We said that the change in momentum, I could say delta p, that's also delta mv, of course. That's going to be minus 2 mu. So that means that the force exerted on this wall by this ball is going to be minus 2 mu over the collision time. That is how long it's in contact with the wall. The longer it's in contact, say it's a really deflated football, then it's not going to be exerting much of a force. If that's a massive ball bearing, then the collision time is going to be very short. So that means t is small, the force is going to be quite big.
Change in momentum is also known as impulse. So whenever you see impulse, it just means a change in momentum. Same units. So if F equals change in momentum over time, there should be a delta before the t as well, but we leave that out. And we said that this is impulse, given the letter I, then that means that force is equals to impulse divided by time. Same thing, just that impulse is change in momentum. You might get given a graph. This will be a force time graph. Now whatever shape the graph makes, you know that the area under the graph is equals to the change in momentum, or the impulse. Just like if we have a speed time graph and we find the area under the graph, we find distance. Here, if we have force and time, find the area under the graph and we find the impulse, the change in momentum. As per usual, split it into rectangles and triangles. So I split this into two triangles, base times height divided by 2, base times height divided by 2. Add them all up and you find the change in momentum. Usually, whatever is experiencing this change in momentum starts at rest. So that means no momentum at all. So by the end, the momentum that this object has is going to be the area under the graph because it didn't have any to begin with. That's going to be equals to mv. Then if you're trying to find the velocity, just divide the area under the graph by the mass and you find the speed.
Now let's talk about one situation that confuses quite a few people. Let's talk about a hose pipe where we have water coming out. If this water then hits a wall and it stops dead, if it comes back, obviously we have a greater change of momentum than it's just momentum. If it stops dead, we don't really have a collision time because there's a constant flow of water. So how on earth are we going to find out what the force is exerted on this wall by this stream of water? By the way, it doesn't matter if there's a wall or not. If there isn't a wall, the question will say something like, calculate the change in momentum every second, which just means effectively find the force. Let's write down our equation. F equals delta mv over t. Now then, if the water is flowing out of here at a constant rate v, then obviously v isn't changing at all. So let's take v out of the equation there, and instead we've got delta m divided by t there. This is true. The force exerted on the wall by the water if it stops dead is going to be the speed of the water times the change in mass per second. In other words, kilograms per second. This is one time where units are definitely your friends because you will not get given an equation for this, but we're going to derive one now. Now I can tell you that this hose pipe has a cross-sectional area A, and the water has a density rho. That's not a P, that's a rho. It's a P without a little ear. Now area has the units meters squared. Rho has the units kilograms per meter cubed. Now we want to get from these two to kilograms per second, and we need to times by meters cubed, because of course there's no meters cubed in here at all, there's no meters at all, and we need to times by s to the minus 1 as well, because we have that. So where are we going to get our meters cubed from? Well look, we have meters squared up here. So let's do A times rho, or rho times A. That gives us kilograms per meter. That doesn't really tell us much at the minute. We need something else. We need to get rid of this meters to the minus 1, and we need to add our seconds to the minus 1 in there as well. What do? We times by the velocity. Rho AV gives us kilograms per meter times meters per second. Those cancel and we get kilograms per second. So the change in mass per second for a fluid coming out of a pipe of cross-sectional area A is rho AV. To turn that into our force there, all we have to do, of course, is times by velocity once more. So we end up with rho AV squared. This is a bespoke equation with respect to what we're given in the question, but quite often you might not be given density, and so you'll have to work through this whole process of figuring out what units you actually need to end up with in order to find out the force. Make sure you write down the units of all the information that you're given in the question, and I guarantee that it will become clear. So I hope that helps. If you have any questions, please leave them in the comments below and I'll try and answer them as soon as I can. See you next time.